quantum mechanics, black holes, genetic regulatory networks, systems biology, ecosystem science, artificial intelligence, and machine learning. Science, math, logic, probing the mysteries of time and space. Get your nerdy talk here with everyone's favorite scientist on Talk Nerdy to Me.
Well, good morning, ladies and gentlemen. Dr. James Lyons-Weiler coming to you live from the WWDNYK studios. WWDNYK, for those who are uninitiated, stands for What We Do Not Yet Know. WWDNYK, What We Do Not Yet Know. So we're living on the edge of knowledge, and that's a very fun place to be. Today, we're going to be going into a different direction than I have so far in the past. I've started on the Big Bang. We're going to eventually be going into the subtleties of quantum physics. That field seems to be exploding with new ideas, new information, new models. But today, we're going to be discussing an interpretation of a finding from 1977. We're going to be talking about the WOW signal. This was a narrowband radio signal that was discovered it was received on August 15th, 1977 at Ohio State University's Big Ear Radio Telescope here in the in the United States. There was an astronomer who was tending to the data, and the computer printouts would be collected daily, and he'd be given to him or every other day or so. And he would go through these printouts looking for anomalies in the data that suggested perhaps the telescope that they were using as a radio telescope may have picked up the signal. So let's look at what that setup was. First, they're looking into space. It was in the night. They could have looked at any time of day, I'm sure. The Drake equation actually tells us that there should be a large number of planets out there in the universe that have intelligent life, that are capable of having technology that release technologically signals of technological origin that leak out into space or are sent out into space, revealing the existence of these other planets, these other civilizations. And this Drake equation has been around for some time. It's been modified and extended into a statistical equation. But nevertheless, this is the setup. Astronomer Jerry Ehman discovered the anomaly from the radio telescope called the Big Ear. And I'm going to go into a little bit about the technical setup of the Big Ear. In 1977, he was looking at the sheets, and he circled the signal there and wrote, "Wow." Basically, any signal coming from space would hit a flat reflector, which would the radio signal would bounce off to a parabolic reflector, which would then go into both of two feed horns. The feed horns are the detection instrument on a radio telescope. The signal, I understand, was detected in one of the feed horns, but not in the other. And we're going to discuss what that may or may not mean with our guest. But if you look at the WOW signal, to help people understand and interpret what the WOW signal is, you have a pattern, a numeric pattern. This was an encoding created by humans. The numbers don't come from outer space. The encoding of radio signals reaching a certain intensity of what's called a signal-to-noise ratio. And the signal-to-noise ratio has two important attributes. The first is the intensity of the signal-to-noise ratio, and the second is the duration. And these letters that are represented by this code that the astronomers adopted to make it human legible and easily interpretable brought about this exclamation point after the WOW, because it was a very strong signal. So my guest today, that I'm very happy to introduce you to, is Alberto Cabarello. He has an MA in Intelligence Analysis and Counterterrorism. He is the host of the Exoplanets channel. a YouTube channel about habitable exoplanets, extraterrestrial intelligence, and interstellar travel. He is also known for coordinating the Habitable Exoplanet Hunting Project, an international network of more than 30 observations looking for nearby potentially habitable exoplanets. The team recently reported GJ3470c, the first exoplanet candidate fully discovered by amateur astronomers. In his last paper, Caballero proposes a new type of crewed interstellar, crewed being that means it has human beings in it, crewed interstellar spacecraft called Solar 1, which could theoretically reach 30% the speed of light. So there's his channel. He was recently interviewed, and I highly recommend this interview, on the Event Horizon by John Gaudier, where he goes over in great detail all of the technical aspects of his inference, and we're going to be going over some of that today as well. So please welcome Alberto Cabarello. Thanks for coming on Talk Nerdy to me.
Hello, thank you very much for having me today here. It's a pleasure.
Right. So the first thing I wanted to ask you was a little bit about yourself. At what point in time in your life did you decide that searching for the evidence of interstellar exoplanets, when did you become interested in other civilizations and signals from exoplanets?
Well, my passion for astronomy actually became around 5 years ago. I started becoming interested in astronomy in general, everything related to astronomy. The first day wasn't my interest on exoplanets didn't start the first day, but I started with astronomy, space, this kind of general topics, and then I started moving towards the area that was most of my interest, which ended up to be exoplanets. Actually, I believe everything is quite related, because if there is extraterrestrial intelligence out there, they're probably living in an exoplanet. Well, maybe they might be living in a spacecraft if their star system has been destroyed, or the life has ended in there, or something like that. But probably in an exoplanet, and interstellar travel is related as well, because if humanity wants to get there, they need to figure out a way to actually get there with a spaceship. So I think all these topics. So once I became interested in exoplanets, later I became interested in the rest of them, because all of them seem to be related. Yes.
Okay, so how often do radio astronomers, or any type of how often do we pick up a signal that looks like it could possibly be a signal that could be interpreted as a signal from an exoplanet with a civilization? Do you know?
Well, we are getting signals all the time. We have a large list of potential candidates. The WOW signal is the most. It remains the first one in the list, because it's our most strongest candidate, let's say. But still, the probability, there is a scale in terms of probability. How likely is that signal could actually come from an extraterrestrial civilization? The probability is in general really low for all the candidates. Even if they are considered candidates of SETI, they are called SETI radio candidates, SETI radio signals. They are candidates for extraterrestrial intelligence. We have a list, but all of them have a really low probability, especially the WOW signal, for example, which is our first candidate. It never repeated. The signal never repeated. So that's the main aspect of a signal actually came from an extraterrestrial civilization, that it must repeat. If it doesn't repeat, it's the probability goes really low. So we have astronomers, for example, from the SETI Institute. They have the Allen telescope array, which is quite a large. They have an array of several mirrors, radio telescopes. Sorry. they are getting signals all the time. They are getting candidates. I'm not sure about the frequency, but probably every month. Even one of the observatories in our project, he actually observes the WOW signal region, that part of the sky with his amateur radio telescope, and he gets candidates all the time. He has a website and he has a list of all the candidates he's getting, and it's quite a long list of possible candidates, and he only has a 3-meter telescope. His radio telescope is only 3 meters, so you can imagine what the big telescopes are getting, but all of them are just candidates with really low probability, so nothing really interesting. Once someone finds something that really repeats, and everybody will know it.
Yeah, absolutely. So, it's fascinating because if we find a signal that repeats, if we find a reliable source, of course, the cryptologists will seize on the signal to try to decode it, see if there's any structure in the data, right? So this would be fascinating to see. But to me, it's fascinating because this would mean biology. Well, first of all, I want to back up and say most people who have thought about astrobiology, exobiology, have looked at the Drake equation, considered the likelihood and so on, and said, yeah, life is probably not unique to this planet. However, simple life, the development of technology, the development of civilization capable of technology, the development of intelligence with awareness that there are other beings. So the way I put it is, if we find a signal that reproduces, it's shown us that there's biology elsewhere that has become conscious and technologically able to create the technology. And there are also awareness of others. This idea of a conscious that's awareness of others, that it's sufficiently sophisticated to develop specific technology to transmit information from place to place. Not specifically to us or to outside their planet, but at least they're transmitting information, they're communicating with each other. And the fundamental nature of that signal would be profound. I mean, this says that there are organisms out there of unknown biology, of unknown tolerances, of hospitable habitat that specifically needed to communicate from one location to another at a sufficient power for us to be able to detect it, which is, there's a number of filters on there that tell us this is really unique and special. So if you don't mind, Alberto, could you help me decode the signal to noise ratio diagram here for the viewers?
Yes, basically, well, I mean, I believe the radio telescope was only gathering data, updating the data that the feed horn was receiving every 15 seconds. It was not in the millisecond range. For example, one of the observatories that I coordinate, he gathers data every millisecond, and he would have been able to actually have all the data for that graph. Yeah. But in the big ear telescope, I think they were only gathering data every 15 seconds, 20 or something like that. So that's why it has really a low number of data points, and basically it has that form. The graph has that form because the radio telescope was not pointing at the star, at the region of that. The telescope was not pointing at that part of the region, of that part of the sky all the time. It was just sweeping. It was just scanning all the sky, and that's why the intensity of the signal actually started increasing. And then when the telescope was moving away from that part of the sky, the intensity decreased. So it was only 72 seconds because that was the maximum time that the radio telescope was able to scan, to look at a specific part of the sky all the time. Only 72 seconds until the telescope moved to another part. So probably the signal would have lasted longer. We just didn't. They don't gather the data, but probably the signal could have been even longer. But it's important to note that the observatory analyzed the data several months later, I believe. So they were not able to actually, maybe the signal repeated even before or after they detected the signal with the fifth horn, but it was a period of time between the detection and the analysis of the data, so the signal could have actually repeated afterwards. And basically, yes, they assign the number one is basically I would say it's background noise. It's just interstellar noise, and they assign for the frequencies, for the intensities, they assign numbers from 1 to 10 in increasing intensity, and then they started with numbers A, B, C, D. That's why we see E, Q, U. I believe the largest intensity in that code would be U. So that's basically the way they used the numbers to represent the intensity of the signal.
Okay, great, thank you. That was excellent. So, looking at that chart, the telescope is fixed to the ground, right? So it was moving because the Earth was rotating. Is that correct? So
yeah.
The radio telescope itself didn't move; it was fixed to the ground. But as the Earth moved, then it swept that part of the sky and it picked it up. Fascinating. Thank you for that. So you've already said that the signals appear all the time on a regular basis. There's a growing list of candidate signals that all have to be interpreted. They all have to be looked at. What you did with this, I think, is groundbreaking with your paper. This paper, an approximation to determine the source of the WOW signal. What you basically did is said, okay, listen, we know the region of the sky. Here's the abstract. You know the region of the sky that it was pointing to, and you're interested in narrowing down out of all the stars that are present, the stars that are out there that are likely sources, the most likely sources, if the WOW signal is real. And what that means is your paper doesn't demonstrate that the WOW signal is real. You're simply saying, okay, guys, if the WOW signal is real, here's a procedure by which we could narrow down to candidate stars that we might want to pinpoint our focus on. These are the ones that you want to sample more exquisitely as technology develops, looking for signals. Is that your goal here?
Yes, exactly. I mean, the WOW signal region has been scanned many times, but by many observatories. So, I mean, it's an indication that maybe it was not it didn't have an extraterrestrial origin, but it may have had, because, for example, the signals that we have sent, humanity has sent radio signals to potentially habitable exoplanets in an attempt to contact a possible civilization, and we have sent the signals only once, twice in a matter of hours. So it's like maybe they would have sent that signal as well, and just once. So it's the same we do, just without just once we send signals, just individual signals, not repeating them. Basically. Sorry, what was the question?
Yeah, no, the question was, your motivation here wasn't to prove that the WOW signal was correct. In your paper, you presented a methodology, basically, of inference that allows people, if we have a good candidate, we can drill down into G and K-type stars. So let's back up and please define a G-type star and a K-type star.
Yes, well, basically a G-type star is a star which temperature goes between 5,200 Kelvin and 6,000. So any star with a surface temperature between those intervals is considered a G-type star. And basically, and a K-type star goes from it's a star which is that is smaller than the G-type. Our sun is a G-type star, so a K-type star is a star that it is smaller than a G-type. The temperatures go from, I don't remember, 4,000 to 5,200, something like that. I don't remember exactly. And basically, K-type stars are actually believed to be more better for life as we know it, because the lifespan of a K-type star is actually longer. And there have been some papers, there is some research pointing out that superhabitable exoplanets, which are planets that could be more habitable than Earth, they would actually they would actually exist around this type of stars, K-type stars, instead of G-type, because they have longer lifespans, and basically because of that. And but the problem of K-type is that they emit more X radiation. So it's not in any. So that's why I chose when I was looking for stars in the low signal region. I preferred to choose only stars from mid K to G type. So I removed from the sample, I removed all the K type stars that are very small, because in general they emit more radiation. And red dwarfs, which are the smallest ones and the most abundant, they emit even more X radiation. So for life as we know it, yeah, radiation might not be good, but some K type stars could actually be more super habitable. I mean, super habitable in terms of life being more abundant there, but not necessarily life as we know it.
Right.
So that's the key point. They might have more life than we have on Earth, because on Earth we have deserts, we have Antarctic. The Antarctic, I mean, there are some regions which is really impossible to live. And right now, with the climate change, Africa is getting really, really hot, and it's been a real problem to live in many parts of Africa because of the lack of water, etc. So yeah, maybe super habitable exoplanets around K-type stars could have more life than Earth, but probably different because they have more radiation. As what you said, is that what I wanted to do is exactly that. I wanted to actually say, okay, if the signal came from that's my main hypothesis, my main assumption, that the signal could have come from an Earth-like planet. If it came from an Earth-like planet, probably the star is a sun-like star. So that's why I decided to actually propose this. To look for, I decided to look for sun-like stars because this may actually encourage people to look for exoplanets around these stars, rather than continuing the search for. It's another possibility, pointing a radio telescope exactly to that star, but also looking for exoplanets and trying to see if there are habitable exoplanets around these candidate stars.
Yeah, so what you're saying is, look, we've got this. We're scanning all the time. We get these signals all the time, but what are we going to do about it? What comes next, right? And I like that. I like that a lot. My postdoctoral advisor, Masatoshi Nei, he's an evolutionary biologist, a molecular evolutionary biologist. He didn't like the term extremophiles. Extremophiles is a term that's used to describe organisms that live in the extreme environments, like thermal hot springs, or in the deserts, or in the Antarctic. And his perspective was, if life exists, it will find a way, right? So I agree that it's fascinating to potentially find the G and K type stars that would have radiation intolerant life. I guess we can call it that, right? That's less radiation intolerant. But Radiolarians is an organism here, a microorganism that's extremely capable of tolerating radiation, and he used to point to that all the time. So I understand what you're doing. Let's find Earth-like stars that are like ours, that might have Earth-like planets, so that if they're similar to us in biology in some way, at least in the range of tolerance. And I think that's an interesting approach. So let's take the viewers through the series of inferences, if you don't mind, that you use to drill down the list of stars, starting with the region of the sky detected. Why are there two regions here? Do you know that might be candidate regions here?
Mm-hmm. Yes, there are two regions, and the signal could have come from any of the two. Yes, we don't know which one.
Right. So the radio telescope focused on the regions, and this is from your paper. This is a list of stars that would have been potential candidates within one of the two regions, right?
Yes, exactly. I believe that's the list from the positive fifth horn, which is the one in the left, probably. I'm not sure, but
Right.
one of the two fifth horns. I mean, and that's those in those little parts of the sky. There are tens of thousands of stars. It's huge the amount of. Actually, in the Gaia, I used the Gaia archive, which is a catalog made by the European Space Agency with billions of stars, and they are only show 2,000 stars in the when you are actually looking through the data, going through the data. They only show you 2,000 stars at a time.
Mm-hmm.
You can actually filter the stars, filter all the stars, so you actually get all the data. But you are only able to see 2,000 every time. So you can actually get an idea of the massive amount of stars in those little regions.
Great. So the next kind of drill down then, as the idea, you narrowed the list down from all the possible stars that all the listed that are in the list down to more likely stars that follow the criteria of the type of star you're looking for. And one of your criteria here included the temperature of the star. So can you explain the temperature and luminosity diagram here? Temperature and luminosity.
Yes, well, this is the conservative sample. I differentiated. I made two samples. The optimistic sample with I think 66 stars. With when I filtered the data for stars with temperatures between 4,000 and 400 Kelvin and 6,000. That's when I was saying, like K-type and G-type, all of them, part of the K-type stars and all of the G-type, and I found 66. But 66 stars for which we have the data for the luminosity. That's the problem. Only around half of the data has information about the luminosity, or only about half of the stars. And in this conservative sample, I found around 15 stars, which is the graph you are showing, only 15. And these 15 stars actually have both temperature and luminosity. So as you can see in the graph, there are the lines are actually intervals of error, error in the measure. So basically, I calculated the error. Well, I didn't have to calculate it. It's all in the database. I put the error for all of them, for both the luminosity and the temperature of every star. And as you can see, there are only 3 candidates which luminosity error, the interval of error for the luminosity, let's say, includes the temperature of the sun. The temperature of the sun, which is 5,780, I think, only falls in the interval of error of luminosity for 3 candidate stars, which is actually those 3. The blue dot belongs to the main candidate, and the green dots, which are below the blue one, are the other candidates. And the rest of the stars, they could be sun-like, but the error of the luminosity, the intervals, are outside. They don't include in the temperature of the sun, so that's why they are less likely to be sun-like stars. And the problem is that these are only 15 stars. There is another list of around another 15 or so that I only found the temperature for them. There is no luminosity, so many of them could also be impossible to know.
Understood. So in your figure 7, then you're bringing in another criteria. Well, you show just based on the temperature, this interesting selection here. You've narrowed down to a star that is basically a clone, if I understand it, on these characteristics of our own sun. Is that right?
Yes, many of them. Well, in this case, it's more difficult to say that they are probably sun-like, because we don't have value for the luminosity, and that's crucial to determine whether or not a star is sun-like. Luminosity is crucial because, for example, the sun, our sun, throughout the years. In 1 billion years, 2 billion years, the temperature of the surface will not increase very much. It will stay practically the same in 1 billion years, 2 billion. But as the star gets older, the luminosity and the intensity. The luminosity goes really, and the radius increases by a lot. There is a huge increase in luminosity and radius of a star as it grows older, but the temperature remains the same. So that's why it's really key. And a key aspect is really important to actually have the luminosity. But for these stars, as you can see, the green dot belongs to the main candidate, and then the blue dots are the stars. Exactly. The blue dots are stars with only known temperature, and the orange stars are those with both temperature and luminosity. So this graph actually combines both the previous graph and the graph with only and those stars with only temperature. And the interval of error, as you can see, it's not the same in all of them. The main candidate star, has an interval of error between 5,500 Kelvin and 6,200, more or less. And there are some stars with a temperature error, smaller. Mm-hmm. But the problem is that we don't have the luminosity for them, so it's impossible for us to know. So the Gaia archive, the European Space Agency will release new data in 2022. So in 2022, I will try to see if we have more information about the luminosity of all other stars, because maybe I have to change the main candidate.
Okay, Alberto, let me ask you, let's go back to the nature of the signal. So I understand that the signal is within the range of neutral hydrogen. This is the relationship, the actual frequency transmission is tied somehow to the 1,420 megahertz region that ties to neutral hydrogen. Is the thinking that this is significant because if intelligent life is to communicate across the chasm of space, that they would choose a frequency that other intelligent life might also choose to use and to seek signals at?
Yes, exactly. I mean, the frequency of the wave signal is actually the hydrogen line. It's because there is the water hole, which is contains a range of frequencies. It goes from the hydrogen line to I don't remember the name of the compound. It's hydrogen H, and the other compound it's O2 or something like that. So that's why it's called the water hole, because it's H2O. But the hydrogen line is only for 1,420 point, more numbers, and this signal is actually exactly in that frequency. And it has been actually, it is believed, but by the scientific community, that if there is an extraterrestrial out there, an extraterrestrial civilization out there, they are more likely to use this frequency because, because of it's symbolic. It's a frequency that it's symbolic because it represents. It represents the hydrogen, which is believed to be the most common compound in the universe. But that's something that because we also have dark matter, which is believed to be much more abundant than hydrogen. But if dark matter exists, it would probably have a frequency. So maybe an advanced civilization, they are using, instead of our frequency for hydrogen, they are using another frequency. So it's really, but yeah, of course, there is a window in terms of frequencies between 1 and 10, I think gigahertz. Between 1 and 10 gigahertz, there is very little noise for our radio telescopes, because to until 1 gigahertz, you get a lot of cosmic background noise. and from 10 gigahertz you start getting a lot of noise from from the atmosphere. So basically, from 1 to 10, it's a really good window. And yeah, basically the hydrogen lamp, because it's symbolic.
Right, so it's kind of iconic. You're also displaying that, look, we have technology and knowledge. We understand some of the fundamental aspects of physics, right? We understand what hydrogen is. We understand what hydrogen frequency is. So there's an embedded signal there that if a signal's coming to the planet, or if we send a signal out, we're basically signaling, hey, we're here. We have arrived at a particular level of civilization, a scientific understanding of the world and the universe around us. But I was not aware that there was less noise in that band as well, which is kind of convenient. Yeah, suppose if I were to be asked, Dr. Lyonsweiler, we're going to be sending a signal out, which we'll get to the question on the moral virtue of doing that later, but in a bit. But if I were to ask, how would you do it? I think I would choose multiple bands, multiple frequencies that represented confirmation that we're doing it according to the periodic table of the elements or something like that, right? So I would choose some other iconic frequencies that would spell out, that we understand carbon or cesium or some other thing as well. So the probability that this signal was just a spurious thing that from nature in the universe, a false positive, would be very, very, very low. And I would also pattern it. I would pattern it like we do with Morse code, with a very short window of time, knowing that people out there in the universe, I call them people, but species are sweeping the sky in short periods of time. It's like, I would send a pattern that would be very distinctive and repeating and things like that. Just like we've seen in the movies, like Contact. So these are not new ideas, I suppose, but that narrow frequency. Let's talk about other possible sources that have been postulated and the current status of knowledge of, I understand one of your colleagues has proposed that potentially there is a source, let me see, I want to bring this up here, of a comet. So if we can just skip ahead a little bit, this is Claudio Macconi. And let's talk about the idea that he proposed that this may have been a signal from a comet in the sky that was ostensibly pretty close to where the comet should have been in order to be the source of the signal. So is the comet a likely explanation in your view?
I don't think so, but just because of the fact that the comet passed through the region at a different time. It didn't pass through the WOW signal region when the signal was detected at that time. So it has been refused by most of the scientific community, including the discoverer of the signal, because of that, and actually because of more reasons. Because the frequency would be unlikely to be exactly that frequency. Comets emit in another frequency, and also I don't remember. There are several explanations, but the main one I would say it's because the comet passed through the region at a different time. So, but yeah, I mean, maybe if the comet passed at that time, maybe it could have been the source. Of course, who knows? I mean, hydrogen is the most common element in the universe. So, I mean, we don't even know. We are starting to understand how interstellar asteroids work. When Oumuamua left the solar system in a strange manner, quite fast, we were actually surprised. So we don't know 100% how the solar system works. Even asteroids coming from outer space, which we are actually studying right now. I mean, we detected the first one, Oumuamua, recently. So we don't know. Probably everything in the universe is quite similar, but we don't know for sure.
I agree. We don't know. Outside of our own solar system, we're just discovered this year that the solar system is more dense with particles than outside of our solar system than we suspected. And it makes sense if you think about it. All the planets and asteroids, etc., all the matter that's in our solar system is sweeping up all of the particles due to gravitational attraction. So the farther away you get from the gravitational center of the solar system, you have more of a dense soup of particles. It's not a pure vacuum, that's for sure, but it's close to a vacuum. It's considered a vacuum. Say if you're halfway between the Earth and the Moon, you basically in a vacuum. There's still a small number of particles that are present, but the outside the solar system. So yeah, you're exactly right. We do not yet know whether certain aspects of the universe are constant, but we know that hydrogen is probably everywhere at least in the observable universe. So all right. So if it's not the comet, the candidate comet, what about the idea that there was a satellite that was passing over at the time that was emitting signal?
Yeah, I believe that has been dismissed as well because the good thing about satellites is that we can track them. We can know when every satellite passes to every part of the sky at a certain moment. So I believe satellite was immediately discarded, actually because of the frequency. For example, one of the observatories I coordinate, he tells me that he doesn't have any problem with satellites. He knows in which frequency these satellites emit, and he tells me that he has never had any problem with that. No, so it's like basically satellites would not actually, and actually we're talking about a signal with a duration of several minutes. Satellite probably passes really fast from that part of the sky. So I'm not sure. But actually, the number of satellites right now it's much higher compared to back in the 70s. I guess so. Yeah. Right now, it's probably it can be a problem. The thing about satellites, receiving a false signal from one of them. But back in the 70s, probably I wasn't born, so I don't know. But I guess that the number of satellites was smaller. So I would say that's probably dismissed as well.
Okay, so what about something internal to the radio telescope itself? A source of noise that, like an earthworm crawling across an element or something like that could explain that there's some conductance between. I know the design of the array. You have a wood insulator so that you don't get this kind of transmission. But what if something like an earthworm crawled across the metal, or a snake crawled across the metal, connector, right? Something, Earth origin signals. We can't rule it out. It's a hypothetical. I don't know the full design, but what do you think about that?
Well, I've never thought about that, about an animal crossing the. It's interesting. But I don't know. The signal is actually it seems to have all the properties of a signal coming from deep space because of how actually the Earth is moving. So the signal actually shows a clear pattern of intensity, and it seems like the source was actually continuous. The intensity of the source was actually continuous, and there is an increase and decrease in the graph just because the Earth is moving. So it seems that the signal was quite continuous. So I would also discard that as a possibility. But of course, the possibilities are there could be many possibilities because coming from outer space, we don't know what is. There are many interstellar clouds, which it's unlikely to have caused this, but the hydrogen is the most common element in the universe. We don't know what is out there. It's like fast radio bursts. We don't know what they are. We know that they happen as much as 10,000 fast radio bursts every day from all parts of the sky, everywhere. So we don't know what they are, but they are unlikely to be extraterrestrial because they are really common. And so I would say the WOW signal could also have had a natural origin, but we don't know yet. But it could also be artificial. We don't know.
Yeah, very good. So some people say that you and I are talking about this particular signal because Dr. Ehman wrote, or Mr. Ehman wrote wow on the paper, and that it's kind of some kind of successful unintentional branding, that it's catchy. That there's a selection bias. I mean, we talked about how there's thousands of potential candidates to look at, but and you said it yourself. It's just something that's famous. It's but it's more famous because of the duration. There's 72 seconds of continuous radio transmission. Has anybody tried to decode that radio transmission in any way? Look for any structure, any information? Information scientists should be able to look at radio transmission to see what the distribution is, and see if there's any message encoded in it.
Yeah, I believe there have been no papers actually going in that direction. I tried to actually see if I could decode the signal, but I didn't find any way to actually. It seems like a sort of like a burst of continuous energy, without I would say like a radar, like a signal from a radar without any information. So I actually, there is a picture, there is an image showing the signal in a real image of. I'm not sure if you have it. It's I would say it's really difficult to decode that, because maybe that's the key aspect. Maybe the signal actually had some information in it, right, but maybe because of how far. Exactly, yeah. Maybe this signal had information, but because of how far the signal was, maybe we are not able to decode the signal. Or basically, maybe that's just part of the full message. Maybe because the Earth was moving, and we only scanned that part of the sky for a couple of minutes. So maybe this is actually part of a larger message, which we didn't detect, and actually happened. It actually came to the Earth before the detection and after the detection, a few minutes later, for example. And maybe if we had the full picture, we would have been able to actually decode the message. But only with this little part of the whole picture, maybe I would say it's impossible. It's really difficult to decode. And as I said, maybe it could have contained, because that's the problem. If you are emitting, if we have sent radio signals out there, sure, with messages, but some of the places to which we have sent the signals are really far. So maybe they will get the message we have sent, but just in the form of a burst of energy, something like impossible to decode because of the far distances involved. So I think it's all about distances. It's really, I mean, because the inverse square law, the longest the distance, the less intensity gets to that to the destination. So the more distance, the more difficult it is to decode anything, and the less it would look less like an extraterrestrial signal the further the distance, I guess.
So it's fascinating that you said that it's like a radar signal, because it seems to be basically a homogeneous signal, not something that has modulated information inside of it. That so that frequency analysis, Fourier analysis, spectral analysis, I guess is what I'm saying. Yep. That you would look at the frequency distribution of intensities within the 72-second window and see if that has the footprint or the fingerprint of communication, or just some kind of noise. I would love to know if that was ever done. Maybe we can look at that again together sometime. So another question I have. Go ahead.
Oh, no, I was just saying that because of the fact that the telescope was gathering data, was updating the data just every 20 seconds or 15 seconds, maybe the signal was actually doing some sort of pattern, like going on and off. And we didn't detect it because we were not, the radio telescope was not gathering data every millisecond. So it's really impossible because that what you said, we have actually the messages we have sent out there were actually in sort of like Morse code, like on and off, some sort of like that, no? So yeah, it's like this is the only way to actually show that you are that you are showing some sort of pattern. I would say that is the
Maybe we can send the signal from this episode to some alien planet someday, and they can laugh at us anyway. So
well,
yeah. Well, go ahead.
No. The thing is that we have never replied to the WoW signal. There is a message called the WoW reply, and all the people believe that we replied, that it was sent by the National Geographic Channel through Arecibo, the Arecibo Observatory, and many people believe that this signal was actually sent because it is called the WoW reply. It was sent to the WoW signal region. And it's not true. I mean, it was sent to 3 stars completely outside, very far from this region. So we have never replied, and we have actually never sent any radio message in the hydrogen line. It is forbidden. We cannot use the hydrogen line to communicate with extraterrestrials. We haven't sent any radio messages.
Who in the planet, the entire planet Earth, with all the countries, has the power to forbid us to transmit information? Keep this channel clear. Is that what we're being told? Get off this channel. This is a radio frequency for communication with intelligent life elsewhere. Keep it clear. So it's forbidden by treaty? Is it forbidden by what?
Yes. Well, you can do it, of course, and probably nothing will happen to you. You can do it in secret without. Nobody's. But there are some guidelines, and there are some frequencies that are protected. Most of them for research, for astronomy, and you cannot actually emit. I believe you cannot emit a radio signal in that frequency, and in many others, not only that one. And there are also many frequencies which you cannot actually transmit. You can only listen. So that actually explains why we have always sent radio signals out there, but not in this frequency. That maybe an extraterrestrial civilization is also preventing them. They are not doing the same because they think that for the same, who knows, no? But you can do it, but in secret, yeah.
So it's really funny. If intelligent civilizations keep this channel clear so that they can detect each other, but they won't detect each other because they keep it clear. It's a paradox. So So the question I want to ask is, do you think we should send signals out? I know that there have been some people who, some very famous people who have said that it would be a really bad idea to send signals out because we don't know what we're fishing for.
Yeah. For example, Stephen Hawking said that he disagrees about this. I believe that the common unofficial guidelines in the scientific community is that, first of all, we need to have a global debate before we send anything. And that has, in my opinion, that has not happened. We have sent several radio transmissions to several exoplanets, potentially, actually, some of them potentially habitable. And I haven't seen any global debate, even not even global, just between the experts in the field taking place before. But they have been. That's true that these radio transmissions that we have sent, they were not repeating, so they were not serious. If you want to do something serious, if you really want the extraterrestrials to know about your existence, you need to repeat the signal again and again and again during many weeks, many months.
Sure.
Many of these signals have been sent with really low power. Arecibo had strong power. The transmitter was 1 megawatt, which is quite. But all the rest had actually, for example, I don't remember the name. A telescope in Russia. The transmitting power was really low, so most of them have not been really serious. But still, who knows? Maybe an extraterrestrial civilization is really advanced, and even if you send a radio signal with really low power, maybe they are. So you are still. But so the debate. The thing is that there should be a global debate before. And once, if there is consensus in that debate, I believe that, yes, why not? If there is consensus in the global debate, I believe that it could be a good idea to send. If there is no consensus, maybe we shouldn't, because there is no consensus. I think this matters to all humanity. So that's why I think it's true that it's interesting that everybody actually gives his opinion about this. Because, but again, it's like I think the chances of having a close civilization that is really advanced, I think the chances are low. And actually, Claudio Marconi has gone in this direction. He made a paper suggesting that the closest civilization, advanced civilization, could be around 1,800 light years away. So even if we send anything, by the time that the signal gets there, we might not be even here. Well, probably yes, but it's like, I don't know. And also, we should know that the Earth is really weak. Not weak, but we have the threat of asteroids, which is it's like we have the dinosaurs. And there is a threat, and we are not able. Well, for example, Apophis will not strike the Earth, but it will come really close, and it is a huge asteroid. So we have the threat of asteroids, and we don't have yet the technology of to destroy these asteroids with lasers. We don't have. If it's a big asteroid, we don't have the technology. So I think it could be a good idea to try to see if we try. Well, to see if. Well, I think not help, because you cannot do anything if the civilization is 1,800 light years away. There is no help unless they have faster than light travel, a really fast spaceship able to travel faster than light. It's impossible. But I don't really see the threat, a direct threat, because it's like, well, we don't know about the intentions of a civilization, right. But if the civilization is advanced, why would they want to destroy the Earth? I mean, it's like, I don't really see. It could be a malicious civilization, of course. They could have bad intentions, but I see that as unlikely. If you take the Earth, I could see the possibility of that civilization having a small part of it which could be bad, like on Earth. I mean, but that's the problem. If you give, imagine a civilization which is really advanced, and everybody has the ability to have a spacecraft, or like here we have cars. Well, imagine a super advanced civilization where almost everybody has the ability to have spacecrafts able to reach really high speeds. So maybe the civilization itself does not pose any threat to us, but maybe a small part of it, yes. And maybe that small part of that civilization is able to reach the Earth. So that's that. I mean, I agree with Stephen Hawking to some extent. I think that somehow it's a little bit dangerous. But on the other side, it's like the most, in my opinion, is the most important. It would be the most important discovery of humanity to find life out there. So I think it's important to actually that we try to see if we contact them, and with consensus, of course. First, global consensus.
So one of the planets in your candidate, I've noticed, was 1,840 or something light years away, 1,000 or 2,800. It was quite a distance, right? So this one of your candidates you talked about in your paper was like 2,800 light years away. So that's a good point. Where do I want to take this? There's a couple of things I want to continue on this topic before we go on to your other work. So the first thing is, has anyone or have you thought about taking your paradigm of scanning the sky, drilling it down to candidate planets, and inverting the process so you identify the most likely stars first, and then when we have those telescopes, then they, instead of sweeping, they spend their time specifically pointing, according to an algorithm, a programmed algorithm, to search high candidate specific star regions that have specific stars, or dense areas of those kinds of candidate stars, is to optimize the time. I know SETI did this massive computational thing. I used to run SETI on my home computer, and help with the crunching, but more of a directed search pattern. Has anybody inverted your logic to say, okay, you have all this information, why don't we prioritize the focus search as if there's something there?
Yes, yes. I mean, there are many nearby, well, not many, but there are quite some nearby sun-like stars. And this has been the target for many, many SETI quests, many SETI searches. For example, I don't know, Alpha Centauri, I'm not sure, but Tau Ceti, Delta Pavonis. There are many stars which are sun-like, and they have, I mean, the radio telescopes have been pointing their antennas to that specific stars during many, many months. Um, Actually, in 2015, there was a Russian telescope that in 2015 detected a strong radio signal, which was likely produced by a spacecraft, but it's not. We don't know 100%. So that's the likely explanation. But they were actually observing a sun-like star during several weeks, months, and. So yeah, but with respect to the Bobo signal, I'm not sure. I mean, I know that the region has been scanned many times, probably probably specific stars, but I'm not sure if specific stars, specific regions. I'm not probably the Allen Telescope Array, which is it's direct. It belongs to the SETI Institute. Probably they have been either specific stars or parts, scanning specific parts of the region. Like the Kepler telescope has done. Sorry, the TESS telescope has been scanning specific parts of the sky during 28 days, and then when after the 28 days they move to another region. So probably the Allen Telescope Array has been doing the same with specific parts rather than a specific stars, because we don't know about any star. I mean, there are many stars in that region. So and it's, I mean, if you point the telescope to a specific part, you will actually be able to detect the signal that comes from any star in that region. But of course, the farther the star is from the center, where you are pointing exactly the telescope, the weaker the signal will be. So of course, you will always be pointing the telescope to some star or close to some star, and the signal, if there is a signal from that star, I mean, it will come stronger from that way. And if it comes from a star which is outside, that is, but it's still within the region, the signal, you will be able to detect the signal still, but with less intensity. So I think that they I mean, if there is I mean, it's really difficult to know, because maybe if what I have been thinking, that if the Wolf signal actually was produced by an advanced civilization, so I mean, if it was produced by an advanced civilization and they wanted to contact us, which would be the purpose, if not, why not? They would have probably repeated the signal. But again, we come back to the thing that maybe we didn't gather data before and after those 72 seconds. So maybe it repeated and we don't know. But it probably could have repeated for a long time. So even months. Yeah. So sorry. Yes.
So if maybe they're like us and they're afraid. They're afraid to contact because they think that we're going to come invade their solar system. Right.
Well, that could be a possibility. I mean, the signal could have also been sent by amateur astronomers, extraterrestrial amateur, because most of the signals that we have sent from Earth, more or less, they were not official. They were not sent by NASA. Like in a NASA project, where let's going to send the strongest signal, which is, I don't know, the strongest radar on Earth. It's 30 megawatts or something like that. It's really strong, and let's do it continuously. No, I mean, so far all the signals we have sent have been more or less amateur. It's just, it's like not amateur, because it was one of them with the Arecibo observatory, but all of them without the real intention. So maybe the WOW signal could have sent in this way, not just, well, let's send something without. But if that was the case, the signal was really strong. So if that's the power of just an amateur radio observatory, the power of an official observatory, one operated by the analog of a NASA agency in that exoplanet, would be probably much powerful. So we have been scanning that part of the sky. So if that was the case, we would have probably detected any airport radars, extraterrestrial airports, actually with much more power in their signals. So I discard that as a possibility. So
as well as signal from the surface to the satellites. We're constantly sending powerful signals from surface to the satellites. So we're very noisy as a civilization. We're not quiet, but we're not we're not in that hydrogen band. Another kind of idea that I want to ask your opinion about is there any logic to looking at gravitational wave detector information for signals? Is for some super powered, highly intelligent civilization that could send gravitational wave signals, because that would be instantaneous. We could actually talk with them. If we could create a gravity wave pulse, we could actually send signals in real time, because the effects of gravity is faster than the speed of light. It's instantaneous. I mean, we're talking about a massive energy. This would take so much energy to do. But so that aside, it's just a thought that I had, that maybe we could look into the gravitational wave detector laboratories and see if there's some pattern there that might, some other civilization we know nothing about, that's 1,000,000 times more powerful than we are, 1,000,000,000 times larger. They consume planets for a living or something. Like we said, biology will find a way.
Yeah, probably. I mean, they could actually either that way, of course. But well, it is believed that in SETI, it is believed that extraterrestrials would use would use something that does not consume too much power. But again, if the civilization is really advanced, maybe for them that's not really much power. Like for the thing that is a lot of power for us, maybe may not be a lot of power for them. But of course, that could be a possibility. Also using laser pulses. Because that's the good thing about laser, about sending light, is that it is visible. You don't have to to be looking for millions of frequencies and getting crazy about what frequency they use. Using a laser, you actually produce a signal that is actually visible with the naked eye. Well, maybe they have a different eye, a different vision, but in principle, the good thing about laser is that it will outshine the star by thousands of times. The star would become brighter if the laser pulse is really high. So that's a possibility. There is a paper actually which is called 200 stars blinking at the same rate. It has been discarded dismissed by the scientific community, probably caused by instrumental error. But the scientific team behind this paper was saying, okay, there are many stars that are actually blinking at the same time at the same rate. So there could be a possibility, actually trying, rather than, well, in this case was actually, it was something like a civilization was sending laser pulses to several stars to increase their intensity or something like that. I don't remember. But so that's more complicated than sending actually just a laser pulse.
What would the effects be of a laser beams flashing through space on... Would there be a scintillation effect of light coming from stars? I mean, would we see a pattern of scintillation? Would it interfere with light from other stars? If we take a satellite and shine a laser from one satellite to another, or just out, and if we had the exact right coordinates, and we were looking at the patterns of stars that are behind the laser beam, would that interfere, and would we see laser beams shooting across the universe?
Well, I would say that we would only be able to see the laser pulse if it's directly sent towards the Earth. Because the problem of laser is that it's not like radio signals. Radio signals, the signals really spread quite a lot. I mean, it's like, but the laser pulses are much more concentrated. They have the square inverse law.
Let me do the following. If I have a light bulb,
sure.
Let's say I have a light bulb, my hand's a light bulb, and I put a laser beam in front of the light bulb, the laser light, because it's photons, should interfere in some way and interact with the photons from the light bulb. And so we would see a difference of intensity in right during the transmission of the laser beam. So a continuous laser beam from the moon, say, out in a particular direction would
Yeah.
should interfere with the light from the stars from behind, right?
Well, yeah, I guess. I mean, of course, you have like if you shoot a laser from the from the moon, you will always see. Well, you have actually you have the light coming from the star from the stars behind that light. So there, of course, there I believe that there is an interference, and we actually have similar problems with SpaceX spacecrafts, which emit quite a lot of light, and the astronomers are really crazy because they don't like that. They that light that the SpaceX spacecraft is reflecting from the sun is actually interfering with other stars, and it's like causing really serious problems according to the astronomy community. So Elon Musk, what he has done is actually to reduce the reflection of those spacecrafts, and the astronomy community still thinks that they emit quite a lot. So the problem with this is that he's releasing many of them. So I don't know if that could be a problem in the long term for the scientific community, but of course there is an interference. But if the civilization actually sent us a laser pulse, we would just see the star actually blinking, increasing the light,
blinking, right? Mm-hmm.
And reducing. And actually, there is a SETI project called Laser SETI, Laser SETI, which actually they have already several. They have several detectors, which are able to actually detect really short laser pulses. So they are scanning all the stars in the sky at the same time, trying to see if they detect artificial laser pulses in the millisecond or nanosecond range, or something like that, really short pulses. And so the SETI search is really going on right now in that direction, trying to see if but the problem of laser is that you need more energy because, I mean, you need a quite strong laser. It's not like radio astronomy or like what we have used for submarines, really low frequencies, really easy. It's really low amount of power. It goes really far. With the problem with light is that you need more energy, but the good thing is that it's much more concentrated. So the law inverse square still applies, but is weaker. So you can actually. If they want to send us a signal, they would have probably to send a signal to the solar system, or specifically the Earth. Instead of other directions.
They'd have to actually pinpoint it to our planet, and we're a moving target. So lasers, so that'd be difficult.
Yeah.
All right. So you're interested in near light speed travel of spacecraft that contain humans. So they're crewed spacecraft. Tell me about your thoughts. Tell me about your paper that you published on a spacecraft that could reach 1/3 the speed of light.
Yes. Well, basically, it's a review of previous concepts. For example, there have been several concepts that have been proposed. One of them is the Buzzard ramjet, which is the idea would be to collect hydrogen and to try to collect hydrogen. It would use the Buzzard ramjet would use electromagnetic propulsion. And there we also have light sails. So my idea was actually to try to see if we are able to combine the best thing of each of them. So the main problem of the Buzzard ramjet is when it is accelerating, the electromagnetic propulsion actually produces drag to the spacecraft. The spacecraft the Buzzard ramjet cannot reach high velocities, high speeds, because of the electromagnetic propulsion. The scoop, the Buzzard scoop, which is actually gathering hydrogen, actually produces drag. So then I thought, okay, what if we use a beamed power propulsion, just a huge light sail, and to accelerate the spacecraft with light or a laser, and just the Buzzard scoop to decelerate. So in that way, we are actually removing the major problem of the Buzzard ramjet, which was actually that drag. by using a different method for the acceleration, which is like, and Robert Forward, for example, astrophysicist Robert Forward proposed in, I think in 1978, 1970 something, or 1964, something like that. He proposed a similar concept, which was to use two light cells and a huge Fresnel lens. So he was actually saying that if we point a laser pointing the laser to the light cell through the Fresnel lens, because you need, but the light will actually spread out, and you need the lens to actually focus the light. So he suggested to actually use that, but the problem is that he suggested to use a 1,000 kilometer Fresnel lens, something like, which is not, in my opinion, really feasible. He proposed that the light cell would be 30 kilometers or something like that. So that's why I decided, okay, I'm going to try to see if we can do something similar, but with a smaller light cell. And but my concept is different than his concept, because he proposed, for example, for the acceleration, he proposed to use a secondary light cell. So the light would hit the first cell. That light would hit the secondary cell, would be reflected to the secondary cell, and that would stop the spacecraft. So my proposal in that sense is completely different. And also, I don't suggest Fresnel lens. What I suggest is to use parabolic mirrors to actually. So I suggest to actually send several parabolic mirrors close to the sun. So therefore, you are able to gather light, much more light from the sun, and then those parabolic mirrors would actually send the light to a secondary mirror, which would actually be changing its orientation all the time in order to keep the beam of the light all the time in the light cell. So that would be the main idea of the acceleration. But also, I suggest another possibility could be laser. But the problem with laser is that you need really a high powerful laser. We don't have that technology yet. So that's why I think that maybe using parabolic mirrors could be something easier. But you need I think I calculated like a 6.4 kilometer mirror, which is quite huge. I mean, you don't really need a mirror with the precision of Hubble or the James Webb. You're not using a mirror for actually image anything. It's just a mirror to actually gather light and send it to another mirror. So you don't really need that precision, that quality in the mirror. But still, 6.4 kilometers is a lot. You can actually build several of them, and all of them are smaller ones, all of them around the sun. So there are many possibilities, yes.
So thank you for that. It's fascinating. This is the Solar One paper, a proposal for the first crewed interstellar spacecraft. You're talking about multiple generations. Well, how close is the nearest star? On your spacecraft, how fast could we get to Alpha Centauri, let's say?
Alpha Centauri would be more or less an average speed of 22% the speed of light. Because the thing is that I did the calculations with the energy, the amount of energy that Robert Forward suggested, because I had to actually propose something. So which number? So I prefer to use something that has been proposed before. So he proposed to use 26 terawatts of power. So that's really a huge amount of power for laser, but for light, it's not that much, because if you send those mirrors close to the sun, you actually are able to get that light more efficiently. And basically, 22% the speed of light with those 26 terawatts of power. You reach up to 30% the speed of light. That's the maximum that you can reach with this configuration. But on average, the average speed is around 22. So you would get to Alpha Centauri A or B. I made the calculations with Alpha Centauri A or B, which is 4.4 light years away. You would get there in about 19 years, something like that, 18, 19.
Wow. So we could send a probe, and it could be there in 20 years or so. Wow.
There are many challenges. Yeah, it's cool, but there are many difficulties in this, because first of all, 20 years for the crew would be impossible. I mean, they would the maximum time that any astronaut has been in space is 3 years, 2 years, something like that. So 20 years, it's really we don't know what effects such a long trip would have on. I mean, you would probably need artificial gravity, which is not really far. It's not really difficult to achieve, but we need that, and also you would probably want a hibernation, some sort of cryo sleep, because 20 years it's like
a long time.
It's sort of
go crazy, right?
It's a long time. So hibernation is a little bit more complicated. Yeah,
it's a
little bit more complicated.
We could send a probe that took samples. We could send a probe that took pictures and turned around and came back. I mean, what the setup requires mirrors near the sun, though, right? So you'd have to have something there to send it back. So what's this? All right, so it would be difficult to get the information from a probe back. How do they return?
Yeah. Well,
how do they get back, Alberto? How do we get their guys back if we send them 20 years?
Yeah, well, the proposal that I have made is actually without a way of coming back. It's just a one way. I mean, you need to be really interested in that, because it's just a one way. The reason why I didn't that it's not possible to come back with my proposal is that you don't have any parabolic mirrors in that star system. You don't have a way. I mean. You have the laser on board, but that's not enough for coming back in a relatively short amount of time. But there have been some proposals. For example, the Starshot project from Breakthrough Initiatives. They're actually proposing to send nano spacecrafts, nano satellites to Alpha Centauri A and B, to Proxima B. Sorry, to try to image the star, and to image the exoplanet. And the information, they would send the information back via radio waves. Each nanocraft would have a small antenna, a small satellite, a small antenna, and they would actually send the images, the pictures back to the Earth in the form of normal radio waves. So they would actually have to send thousands or 1,000 nanocrafts, because many of them would probably get lost in the travel.
Yeah.
But the idea, I mean, I'm more interested in the uncrewed interstellar spacecraft. Yeah. Probably uncrewed, without crew, would probably come first. But I don't know. I'm more interested in crewed, so that's why I'm only working in that.
I know there's a lot of people that want to get off this planet. Now in 2020, things are a little crazy. So, okay. So I have a question I'm going to ask you. You may or may not be the right person to ask. Since stars everywhere emit photons, isn't everything in the universe a solar sail being pushed by solar radiation away from itself? I mean, the universe is expanding, and we've got a mystery about why the universe is expanding. And it occurs to me that since everything is a solar sail being hit from all directions, everything has a net vector of solar pressure. Does this explain why the universe is expanding? And have they factored that into their equation?
Well, I'm not sure. I mean, because I'm
sorry, I didn't say that right. Nobody knows why it's accelerating, but after billions of years of solar pressure, of constant solar pressure, I'm proposing that 10 billion years of solar pressure would cause. Everything's a solar sail. Our moon's a solar sail. The Earth, the sun, everything's getting bombarded with photons all the time. Doesn't this explain the expansion, maybe, and the accelerations going on?
Yeah, well, I would say that I'm not sure, but I would say from my point of view is that, of course, there is light hitting the planets, but you also have gravity. The pull of gravity from the sun is really huge. So even if there is some push of light on these planets, of the solar system, for example, I would say that the planets are still there, because they're not moving away because the strong gravitational pull from the sun.
Agreed, totally. So
that's not the point. No, but of course.
The point is that the sun is also being bombarded by photons from other stars. So the whole planetary system is a solar sail, right? Every galaxy is being hit by every galaxy, right? What do you think about that? I've thought about that a while.
Yeah. Yeah, that's interesting. I mean, I never thought about that in detail, but it's really interesting to think about that. Of course, I mean, the radiation, there is cosmic radiation everywhere, and that's light is radiation, and that's hitting all the celestial objects equally. I mean, not equally, but it's you have it there. And of course, the solar system is moving. It's moving. Everything is moving. And actually, it's interesting because there is a list of stars which will be really close to the sun in a few billion years. I mean, there are some stars will be as close as, I don't know, zero point 0.1 light years or something like that. I don't remember that. Some stars will be really close to the sun, to our solar system, in a few billion years. And even Andromeda is approaching the Milky Way, and at some point, both galaxies will collide. I think so.
That's right.
I guess that everything is also expanding because of the Big Bang. If the Big Bang happened as it has been said, a big explosion.
There is nothing. Acceleration. So the Big Bang would set things in motion.
Oh,
but the acceleration is what I'm addressing, and I think that we cosmologists and physicists who are much smarter than me need to factor in the solar radiation. I see everything in the universe as a solar sail. So I was really excited to have you talking about your Solar One proposal to try to segue to this, to say, hey, wait a minute, somebody who knows to you do the calculations. First of all, what if there was no solar pressure? Take that equation out. What would the universe look like with the Big Bang? And not put the equation back in. Does that explain the acceleration? And if so, this is the first time it's ever been proposed in public. It's always something I've had in my head. So
yeah, of course, that's really interesting. Of course, it could be a possibility, I guess. Also, maybe, for example, Oumuamua, the interstellar comet, when it came to the solar system, it actually accelerated due to when it did a flyby through the sun. Because of the slingshot, slinging shot, it's a good way to actually accelerate. So everything, I guess, everything in the universe is passing around. I mean, is passing on each other, close to each other all the time.
Slingshots, yeah, sure. So that makes sense.
Exactly.
All the time. For 10 billion years, that's got to be part of it too, right? Yeah, sure.
Yeah. So maybe that could explain partly. But yeah, it's a really interesting question. I guess that I don't have the scientific knowledge to actually to say it would
start with two objects in space. So go to the deepest, darkest. Yeah. The universe is only made of two objects in space, and they're not radiating. And then they start radiating, and then you do the math and see if they accelerate away from each other, right? So you can have the objects at different masses. You could have small mass. You could have large mass. Over 10 billion years, there's got to be acceleration on everything's pushing everything away from itself at the same time as gravity pulling in. So this may be, I'm an amateur at this. It may be something that, of course, they have it in the equation. It's in some exponent in some buried in some equation that we don't know about. But I think that that's one question I wanted to ask you, because I haven't really shared it with anyone else, because being expert in examining, you're venturing into solar sails, it would seem that this would be a natural thing to consider. Alberto, you're really a joy to talk to, a very thoughtful person to come up with this way to think about examining signals potentially from alien systems. My last question, and this is for a portion of my viewership. Do you think that we've been visited by aliens from other planets ever?
Yeah, well, personally, it's a good question. Of course, I would say it's really difficult to know because, there are some there is some NASA footage about some UFOs, because UFO is actually something that it's real. It has not been identified. It doesn't name. It doesn't have to do anything with alien, but there are some real NASA UFOs footage which are really intriguing. I mean, I think so far the scientific community has not been able. I remember a few weeks ago I was watching near the Grace Station. Neil deGrasse Tyson talking about this. One journalist asked him, "What do you think about this?" And he said, "Well, we don't know. It could be anything. It could be it's a UFO. It could be alien, or it could. I mean, he said no. It could be alien, or it could be not alien. We don't know. So I think that's the most interesting proof that we have of a possible UFO that could be possible an alien spacecraft, because it's something official. It has been recorded officially by Navy spacecrafts with really professional equipment, and how these UFOs behave is really, really strange. I mean, they behave in a manner which is not similar to me. I mean, it's not really familiar to me that way. There are some atmospheric instruments that we use, but at that speed, it could be also, of course, it could be some spacecraft, some secret, project going on in one port by some group of the U.S. military, and the spacecraft, the U.S. Navy, well, the military who was actually flying the spacecraft, they don't have the level to know about that. So maybe it might be a project secret even for those of the military who recorded that. So, or maybe it could have also been a spacecraft, an advanced prototype from another country, maybe Chinese one. Who knows? No, but I would say that I think that we have not been visited, in my opinion, because I don't see enough evidence for that. Let's say. So, but as soon as I see the evidence, evidence like someone indeed can going out of the spaceship and actually talking to us, trying to contact us, then yes. But so far, I have not seen really enough evidence to say it. So far, I would say that probably no.
Okay, so I thought of a second final question. What do you think the governments of the world, of each nation, would do? Say the United States or Spain, or pick whatever government, if they did detect unequivocal signal of communication from aliens, from advanced civilizations, from other solar system. What do you think their protocol would be?
Well, the official protocol is actually to first confirm the signal. You need several radio observatories trying to confirm. It's not valid enough. It's not enough that only one of them sees the signal. Another observatories, first of all, have to actually confirm the signal, or at least another one. And once the signal is confirmed, the guidelines say that they actually can, they can make it public. They should make it public according to official guidelines. Of course, any organization, for example, China has the biggest radio telescope in the world right now. It is called FAST. It is 500 diameter. It has a diameter of 500 meters. And maybe if they find something, they will not say. Who knows? It belongs to the Chinese government. But the good thing is that most of the SETI quests, most of the SETI research has been done by non-profit organizations. Yeah. That's the good thing. I mean, official organizations like NASA, the Chinese Space Agency, or even the FAST, the Israeli telescope, they are not using FAST most of the time for this kind of searches. They are using it for other type of research. So most of the SETI research has been done by SETI Institute, by this kind of organizations. No, so that's the good thing. So that who is more likely to find a signal? The ones who are actually looking for them all the time, or the ones who are just not doing anything to look for them? Because the NASA does not give any money.
The bureaucrats
exactly. The NASA does not give. Exactly. It's much more difficult. If you are looking all the time to a star, it's more likely that you will find something.
I think
so that the good thing is that the SETI Institute will probably tell anybody, because why not? I mean, I believe, probably yes.
What's your website, Alberto?
Oh, well, my website, it's called Exoplanets Channel, but it is hosted in Wix. Wix, it is a website hosting service. So I don't know the full name of the address, but it is in my channel. In my YouTube channel, there is a link to the website.
And what are you working on next? What's your next project?
Well, right now we're working on something called the SETI project. We are several observatories. Radio observatories, amateur radio stations, trying to see if we detect actually extraterrestrial radio signals. And we have selected a few stars, which I thought that they might be interesting. And we are actually trying. One of them is a Finnish observatory in Finland. They are observing. It is the largest astronomical association in Finland. They are observing its star 17 hours every day. And the other observatory in the US is observing around 12 hours every day. So more or less we are covering 24/7. We are observing these target stars all the time, not in all the frequencies because that's impossible, but we are trying to cover, we are trying to see where I find a not intentional signal.
Okay.
Rather than an intentional one, which has been the common quest in the SETI area, right. We are trying to see if we find a non-intentional, which would be much weaker, but we are still trying. We are thinking that what if an extraterrestrial civilization is much more advanced and they use really a lot of power for just normal communications, for airport radars, specifically with the spacecraft. We are trying to see if we detect the signals from an extraterrestrial planet contacting to the fleet of their starships. So it's really difficult, but we are trying it. And if we find any candidate, of course, we will publish. We will publish that, of course.
Okay. Is there any way the public can help fund the research that you're doing?
Well, right now, yes. But rather than funding, people, I'm encouraging people to actually join the project. If you have a radio antenna, a 2-meter or 3-meter radio antenna, and you have a feed horn, it does not really. You don't have to have. You don't need to have a hydrogen line feed horn. You can actually. It can be other frequencies. So if anybody has actually a radio telescope, well, not radio telescope, just a big antenna with a feed horn, they can contact me. They can actually visit my channel. From there, they can actually visit my website, and there is a contact form in the website, and they can contact me. And they are more than. I mean, we would really very happy to have more people in the project, because so far we are only 2 observatories. It's been really difficult to actually find radio observatories for this, because very few people have radio observatories. That's the problem. Optical observatories are much more common than radio observatories. So okay, we are struggling to.
Do you mind if I show your email address here? Can they contact you here?
Sure. Yes. I mean, of course, no problem.
There you go.
Yeah.
So if you have,
it's Caballero. The second instead of E is A.
There you go.
Exactly. Yeah, that's perfect. Yeah.
Sorry about that.
Thank you very much. Yeah.
Quickly, right?
Anybody can do it through this email, and I'm also working on another spacecraft, but that for now it's kind of secret.
I was hoping at some point in my podcast I might have a guest on that says I'm working on another spacecraft. I think that's awesome that you said that way. All right, so Alberto, This has been fun. It's been educational. This is exactly what I hoped for. I'm sure a lot of people are going to enjoy it. This will be uploaded to YouTube. It's present right now on Facebook and Twitter. So happy hunting, Alberto. That's all I can say. Keep up the good work. It's fascinating.
Thank you very much for having me here. It was a pleasure. So yeah, I will be glad to follow up everything. Thank you.
All right, awesome. Thank you. All right, Dr. James Linesweiler signing off until the next time.